All right, this is the third Le Chatelier's principle video lesson, a quick review of what the principle states. You have a system which is at equilibrium, and then a disturbance or a stress is applied to the system. That'll cause it to shift either forwards or backwards to relieve the stress and reestablish equilibrium. Forward shifts will produce more products and use up reactants, while reverse shifts do the opposite. They produce more reactants and they use up the products. Things that qualify as stresses include concentration changes, and that's only for gases and aqueous substances. Solids and liquids, you remember, have constant concentrations, so you can't do this. Temperature change and volume changes qualify as stresses. Remember that, as I just said, solids and liquids have constant concentrations, so they do not result in shifts in equilibrium when you add or remove liquids and solids. Here's another example of a heterogeneous equilibrium. It's heterogeneous because it has more than one phase present, solids and gases. If there's only one phase, if these were all gases, for example, or all aqueous, then we would have a homogeneous equilibrium. We're told that the system is in a closed flask, required because there are gases present. It's at equilibrium. The flask is rigid, which means it's not going to expand or contract on its own. We may have some method of changing its volume, but the system cannot do that on its own. It's an endothermic reaction. Now that could have been told to us also by telling us the value for delta H. Endothermic, you remember, means that delta H, the heat of reaction, the enthalpy change, is positive. Because it's positive, heat is being absorbed, so we'll go and write the word heat on the left-hand side of the equation. If it were exothermic, delta H would be negative, heat would be produced, and we'd write it on the right-hand side. Now the question says, what will happen to the amount of iron in the system? Now, iron is here on the right-hand side. Now let me just point out that it's a solid. However, if the system shifts in the forward direction, you have to make more of everything on the right-hand side. So you'll make more iron. Now notice the question doesn't say what happens to the concentration of iron, because the concentration of a solid would not change. But it says the amount of iron, so the mass or the moles of iron. If you shift forward, you'll have more iron produced. If you shift backwards, you'll have less iron at the new equilibrium system. So what happens if the volume of the flask is doubled? Well, from a non-AP perspective, we would say here that the volume of the flask doubled causes the pressure inside the system to decrease. When you change the volume, you affect the pressure, and they're inversely related. So doubling the volume would halve the pressure. It would cause it to decrease by half. Now, the system then wants to raise the pressure, and it would like to do that by making more gas. So we look at the balanced equation above, and we look at how much gas is on both sides. The iron oxide is a solid, so I'll ignore that. There's 4 moles of gas on the left, and then the iron we'll ignore on the right because it's a solid. There's 4 moles of gas on the right, the 4 moles of water. Now the system would like to it would like to increase the pressure by making more gas, but with equal amounts of gas on both sides, it's unable to do that. So in this question, it's sort of a bit of a trick, there'll be no shift in the equilibrium because there's equal amounts of gas on both sides. Now how would you explain that on an AP exam? Well, you might look at the expression for Q. In this case, Q would equal the concentration of H2O to the power of 4 over the concentration of H2 to the power of 4. I'm leaving out the solids from the expression for Q, just like they're left out for the expression for Kc. They're the same expression, right? The reaction quotient and the equilibrium expression are the same. Now, doubling the volume of the flask causes all the concentrations inside to decrease, and because they are going to decrease by the same amount, we look at the numerator, it's raised to the power of 4. The denominator is also raised to the power of 4. Therefore, the numerator and denominator will both be affected the same way. Therefore, Q will be unaffected by this change. Since Q was equal to K before the stress, Q will be equal to K after the stress. There'll be no shift in equilibrium. From a kinetics perspective, you could argue that doubling the volume reduces the concentrations of all the gases. Therefore, the forward rate and reverse rate are decreased. However, again, the overall order for the forward and reverse reactions is the same. So the forward rate and the reverse rate would decrease by the same factor, and they'll end up still being equal when the new equilibrium, after the stress. They'll still be equal. Therefore, there's no disturbance to the equilibrium. Hydrogen gas is removed from the container. First, from a non-AP perspective, we could argue here that the system is going to try to replace, it's going to try to make more hydrogen gas. Since hydrogen's on the left side of the equation, it's going to shift backwards to make more hydrogen. In shifting backwards, it'll have to use up some of the iron, therefore there'll be less iron at the new equilibrium. From a reaction quotient perspective, decreasing the concentration of hydrogen will cause Q to get larger. Because hydrogen's in the denominator, a smaller denominator means a larger value for Q. So now Q is going to be bigger than Kc, and that will result in a reverse shift. You'll have less iron at the new equilibrium. From a kinetics perspective, hydrogen is a reactant in the forward reaction. So decreasing its concentration will cause the forward reaction rate to decrease. Now the reverse rate is faster than the forward rate. A reverse shift occurs, and you have less iron in the container. If you add iron oxide to the flask, from a non-AP exam perspective, we would simply say that the iron oxide is a solid. Therefore, adding some solid has no effect on the equilibrium. There'll be no change. From a reaction quotient perspective, the iron oxide is not part of the expression for Q. Therefore, adding iron oxide has no effect on Q. Q is still equal to K. The equilibrium is not disturbed. The iron does not change. From a kinetics perspective, the iron oxide is a reactant in the forward reaction, but it's a solid, so its concentration is constant. Adding iron oxide does nothing to the concentration of iron oxide, does nothing to the forward reaction rate. Therefore, the equilibrium is unaffected, and iron is unaffected as well. If we heat the flask, from a non-AP perspective, we would say that we're adding heat. The system's going to try to cool down. The system would like to use up some of that extra heat. Since heat is on the left side of my equation, to use up the heat, we'll have a forward shift in equilibrium. That'll produce more iron metal. From an AP perspective, we would argue that heating up the system causes the Kc in this case to get larger. Because the reaction was endothermic, at higher temperatures Kc will be larger. At lower temperatures Kc would be smaller. If it were an exothermic reaction, then it would have the opposite effect. For an endothermic process like this, then Kc will get larger. That means Q will be less than K, and there will be a forward shift to the equilibrium. You'll get more iron metal produced. From a kinetics perspective, you could argue that the rates of the forward and reverse reactions will increase. However, the endothermic direction is affected more than the exothermic direction. So the endothermic direction here is the forward direction. Its rate will increase more than the reverse rate increases, and that will result in a forward shift, and you'll get more iron metal. Helium is a noble gas, so it's not going to react with anything in the container. Adding some helium to the flask will cause the total pressure to increase. However, it has no effect on any of the pressures that are already there. That's because of Dalton's law. The total pressure would equal the pressure of the hydrogen plus the pressure of the water vapor And now we've added some helium, so plus the pressure of helium. So notice the total pressure does go up, but the added helium does nothing to the pressure of hydrogen or the pressure of water. Therefore, it has no effect on the equilibrium, and therefore no change in iron. From a Q perspective, helium has no effect on Q, therefore no effect on the equilibrium. Q is still equal to Kc. From a kinetics perspective, the helium does nothing to the forward or reverse reaction rates, therefore it has no effect on the equilibrium. If you add water vapor to the flask, water vapor is here, the system's going to try to get rid of the extra water vapor. So from a non-AP exam answer, you would say it's going to try to use up the extra water vapor. To use up the water, it will shift in a reverse direction, and that will cause the amount of iron to decrease. From an AP perspective, you could argue that the added water vapor will cause Q to get larger because water is in the numerator there. Therefore, Q is now larger than Kc. There'll be a reverse shift and the iron metal will decrease. From a kinetics perspective, adding water vapor will increase the rate of the reverse reaction because that's where water is a reactant. Increasing the reverse reaction rate will cause a reverse shift to the equilibrium. That will cause the iron metal to decrease in amount. So there you have it. Le Chatelier's principle, several examples explained in three different ways. A non-AP perspective, a perspective with Q, the reaction quotient, and chemical kinetics. For a grade 12 chemistry class, use whichever of those approaches you like. For an AP exam, be sure that you're using the equilibrium constant reaction quotient explanation or the chemical kinetics explanation.